Physics department, head of department, and probably one of the, or I think perhaps the leading expert on binary star evolution. I don't know if that's right, but I think that's the case. And we're going to learn tonight about some of these women in astronomy during the 20th century. A lot of them overlooked of the contributions they made. A number of them were working for Pickering at the Harvard Observatory, and they were paid a pittance for the work they were doing, really. So, yeah, it's a really interesting topic. So thanks for coming along, Jan. And we're ready to start. Thanks.
Thank you very much, Bill. Kia ora koutou, everyone. Thank you for inviting me back again. I was just reflecting, I've given so many talks here. I've actually had 3 different names as I've gone through and given talks here. And like both as doctor, associate professor, and now professor. So yes, this is an interesting topic. And actually, I've only really discovered these stories over the last few years. And I'm going to try and take a view that I'll be teaching you some stuff about astrophysics, which many of you probably already know. But it's interesting to try and understand the stories, I think, of the people that actually brought this together. And so, yes, you know some of these people, because you probably know Cecilia Payne. You probably know of the Harvard computers. You also probably know Beatrice Tinsley. Does anyone know who this is? No, okay, so we will find out. I should tell you now, but that will spoil the thing. So yes, as Bill already said, Jan Eldridge, she, her, them, they pronouns. I'm an astrophysicist, so I do physics using the stars. Unfortunately, I'm the current head of Department of Physics at Auckland. I say unfortunately because some weeks you go like, this is the best job ever, I want to do it forever, because it's like, you get staff to grow. And other times you think like, when can I retire? Can I retire tomorrow and give it all up? As Bill said, I study exploding binary stars. I'm one of the experts, I guess you can say. Otherwise I wouldn't have got promoted to professor. But I explode the myth of a gender binary as well, because I'm transgender. And one thing I realized is, you all know Carl Sagan, who said recently, well, actually didn't say it that recently, but we're a way for the universe to know itself, because it took 13.8 billion years for the universe to get to today so we can exist and try and study it. We're also part of the universe. And I really like the idea that actually, while we can try and understand the universe, we can also try and understand each other and each other's points of view, which is hopefully something I'll talk about today. And yes, I work on many things, as you'll see as we go through. I also did astronomy because I studied too much Doctor Who when I was younger. If you already know this, I'm really sorry. Because people always ask me, my doctor was the 7th Doctor, although I really like Patrick Troughton, because whenever he goes, now Jamie, the shit's going to go down and it's going to get exciting. But also being Doctor Who is like being an academic, right? Being a professor. We get to explore the universe, take people with us to show them how wonderful it is, and try and make it a better place. But there is less Cybermen and Daleks in academia. So that's always a good thing. In case you don't know, I've actually got quite a large team now. This is both here in Auckland and in Warwick. So my main collaborator is Elizabeth Stanway, who I think has given a talk here before, many years ago. Yes, yeah. Next time she comes back, I make sure I send her down here. And we've got some past postdocs. So John Bray is now back. He was a PhD student, went to the Open University in the UK and is now back. Lynn is still in China, working as a lecturer now. Heloise is got a fellowship at the University of Oxford and doing very, very well. Connor Bryn is Elizabeth's postdoc and currently visiting. And he's another stellar evolution theorist, but is helping us make models of galaxies. And all the rest of these are our students, some of them who you have seen, some are new. And it's just kind of exciting to have this big team of people we work with. So where does this story of building on the shoulders of giants come from? And it comes from me reading this book by Dava Sobel. It actually looks at the history of the Harvard computers and tells the history. And it's, it's one of the very few history books I've ever read, and it's amazingly accessible. And, this covers all of the group because it's quite a large group. And you can read other books on individual members like Cecilia Payne, who is she's a special case I get onto later. But people like Annie Jump Cannon, Henrietta Leavitt, and all these other women, it's always interesting. And this is actually great because you also read of them trying to set up observatories and some of the issues that go on with trying to build in the 1920s and early 1900s, building observatories in remote locations. And it's actually quite similar because it's similar to what we see today in terms of how we have to try and get to a good site to make observations and how we store them. And the story begins not with anyone you know, but with Marianne Draper. So this is the funny thing. Yes, Edward Pickering was the person who was leading it, but the person who paid for it all was Marianne Draper. Her and her husband had planned to actually take observations of the night sky and record in a catalogue, like all the stars in the night sky, and take spectra of them all. Unfortunately, he died, and so Mary couldn't do it on herself. And actually, I don't know why I couldn't find a photo of her and her husband, but I mean, the dogs look great, so that's okay. So her husband is called Henry Draper, and that's where the HD numbers come from today, because it's that catalogue in his name and in his honour that then she paid Pickering to try and do, and actually make that catalogue. Now, the reason why Pickering, sorry, just hitting the microphone for everyone listening on home, that would be really annoying. But the reason why Pickering decided to choose women to do the science is because he had hired some men to take the observations and also do the science. But the men were really bad at the close, detailed work that was required to actually analyze the data. And I'll show you actually in a minute some of the way that what the data would have looked like to actually analyze. And so Pickering retorted, like, even my Scottish maid could do better. I don't know why the Scottishness had to come into it, but anyway, not all of them were Scottish, only Wilhelmina Fleming was. And so he started hiring Wilhelmina Fleming, his Scottish maid, to do the work, and she proved that she was very, very capable. And then, of course, over time, it accreted until you see this very large group of people. Some bigger names than others. For example, Annie Jump Cannon is the one who came up with our method of stellar classification, along with Fleming, who did some of the earlier work, but that's the reason, because someone took over the work, is why it's so peculiar, right? Why we go O, B, A, F, G, H, K. Sorry, K, M. Get that right. But we'll go through and I want to examine a few of the people in this story. But of course, just wanting to recognize that it's a bigger team. And of course, also the problem is that some of them would come along, do this as an unmarried woman, get married and go off and expect to leave the science study, which is a bit of a shame. Now, this is, of course, the professional institute photo. But what happens where you actually go and look at where they actually were working? And this is what they do. And they say these are the devices where you would have the photographic plates, right? So, okay, I can actually say here, because many of you are old, so you know how photos used to be taken. You know, if I'm doing this in schools, it's like, yeah, we didn't have CCDs, we didn't have the camera that Grant was hefting around to take images. You know, you had glass plates. I once got to go to the Carnegie Observatories in Los Angeles, which is really fun, because you go down to the basement and they've got all the glass plates there, and it's like, okay, so this is in Los Angeles when it's earthquakes, and somehow they didn't break any of the glass all those centuries. They've now scanned them all, but it's just, you know, how they made them survive through an earthquake zone is amazing. But anyway, so you put these glass plates on this viewer, you've got a mirror here to reflect the light up, because, you know, you don't have electric lights in those days, and you've got a magnifying glass here because they're actually looking at the spectra for each individual star. So back then it wouldn't be like today where you have an optical fiber taking the light from one star and feeding it into a specific spectrograph. You would actually just have a prism and would make all the stars into spectra, as I'll show you in a second. What's interesting though is it wouldn't just be one person. One person would be looking at the observations and the other person would be writing them down, right? So that's why there's so many people. Although it's like some of them showed more interest in the data, which is why they made the advances they did. And I'm just going to point out here Antonia Maury with this diagram in the background, which we'll come back and look at later because it's kind of important. And you can also see sometimes here they've actually also got a microscope for measuring very fine shifts in the lines. So this is the kind of data what they would have been looking at. And this is what stellar spectra look like. And you can see here that you've got these broad things. So this is actually only in the blue-greeny part of the spectrum. I don't think there's too much red here. But you can see that, oops, where's my light gone? I put my finger over the light, that's why. You can see that some spectra look featureless, other ones have these lines, and some of them actually have emission lines. You can see that little bar there that actually looks brighter than the rest of the stars. And this is really what I was trying to understand. And back in the 1920s, we didn't understand where this came from. We didn't even have the quantum physics of why things look the way they do when they're hot, right? So we all have trouble going to the bathroom, right? Because we think cool stars are red and hot stars are blue, right? So we don't know how to use taps. We all know that problem, right? And, you know, we kind of knew that because we could heat things up on the Earth, but we didn't have the understanding of the quantum mechanics where this all comes from. You know, why these lines are here. Why are hot stars blue and cooler stars red? Anyway, okay, so let's first look at these lines. I'm kind of going to try and tell you what the answer is now, and then talk a little bit about the development of how we actually use these lines to unlock the mystery of what the temperature of the stars were. Because one of the other problems of this is when we're looking at stars back in the 1920s, we didn't have satellites, so we only had the optical spectrum. We had no idea of the radiation coming out in the infrared, and we had no idea of the radiation coming out in the ultraviolet. So again, this was the only thing we could actually work out, and most stars don't output a lot of light in the optical. So a little bit of stellar physics 101. If you have a hot source, it produces lots of radiation, and as I said, if it's at cooler temperatures of 3000 Kelvin, it will look red. As you heat it up to the sun, it will look white because it's 6000 Kelvin. If you go beyond the sun, it looks kind of blue. But if you've got a gas in front of that material, in front of that hot star, it will absorb some of the lights in a fingerprint. And that's, for example, the line of, probably it's trying to show you hydrogen, because that's the strongest one. And what it is, the atoms inside that material have electrons going around the nucleus. A photon of a very specific wavelength, it can only be a specific wavelength, hits the atom and gets absorbed, and so the electron goes up in an energy level, and when it drops down, it emits it in all directions. So the light that's coming towards you is actually scattered quantum mechanically by the atom in all directions. So you see a darkness. Alternatively, if you have an absorption spectra, you've just got a hot gas, which is just emitting the photons at those same wavelengths, because it's being excited, so it's got extra energy to get rid of. And of course, that's scattered towards you, so you see these very bright absorption lines at the same frequency as in the absorption spectra. So we can see this, and it's just telling us something about the atoms there, although we'll unlock more later. So people knew that stars had different emission lines and absorption line patterns, and it was Annie Jump Cannon who really worked out the scheme of trying to combine them. Because if you look at all of those patterns, they're all a bit of a mix-up. And so she realized that the actual important one to look at is the hydrogen, well, okay, William and Fleming came up with the hydrogen line strength being the most important to look at. But then trying to order them into some kind of pattern was quite difficult, and that's what Annie Jump Cannon did. And she was apparently able, by eye, to type 3 stars a minute, which doesn't sound like long, right? So I can tell you here that these A stars have very strong hydrogen lines, right? So you can see that they're there, and they're like the lines space out further as you go along, right? So it's like a unequally spaced ladder. You know, you've got to take bigger steps as you go along, and they're like A stars. If you look at a B star, which is this one, okay, it looks similar, but the lines are slightly weaker. And if you look at an O star, you can just about see the same lines, but they're weakest. And that's why we have the temperature increasing from A, B to O. But why do the lines get weaker as we go that way? We'll work out that in a second. If we go the other way, we've got OB, A, F, F. Now, F is interesting, because if you take, let's take a good F. This F is up here quite bright. If you compare the lines, they're not getting wider in a regular way, are they? They look more like equally spaced. And so that's because it's not just hydrogen there. I think you've got a calcium triplet or a doublet in there as well. And so you've got extra lines that immediately make you see it's something different. And as you go down to, we don't have any Gs. We do have Gs, which actually have more lines, and so they kind of faint. And this is actually a scan of an assignment we used to make our students do, but we gave up because it was too difficult. The students had an hour to try and type some of these stars, and they always got the wrong answer, so we gave up. Even when I give this to fourth year undergraduates now, they struggle for 2 reasons. One is they say, like, no, I just want to use a computer and do it normally. But, you know, they don't appreciate that actually you can do it if you stare at these lines strong enough. The other stars to mention here are Wolf-Rayet stars, which are these emission lines, and that's where they're really hot. They've actually got the hot gas in front. So we kind of know this scheme, and once Annie was able to work out this scheme of the different lines, you wanted to try and place them into some kind of order. And I think part of the order is to do with the fact that we knew the color of these stars, if they was blue, white, or red, because I've got this out of order now, but you can imagine that how you've got hot stuff, right? We know here we've got hot iron being heated up, and you go from infrared here, where we can't see it, and the camera's only an optical camera, to red, to orange, to yellow, to white. So we would have had some appreciation of how hot the stars are and how we can use those lines and the colors to try and place them in the right order. And now, the other thing you need to think about with these stars, and just going into what I said a minute ago, is that why the optical spectra is so important. Even today, we don't have that many space telescopes. We have HST, the Hubble Space Telescope, and JWST, the James Webb Space Telescope. James Webb can only look in the infrared. So these two dotted lines show you where the optical spectrum is. Here's the infrared, and so you can see most cool stars actually output huge amounts of light in the infrared. Sorry, the x-axis here is wavelength in nanometers, and the y-axis is your flux, so how much light is coming out at that wavelength. And so this is why cool stars are red, because they've actually got more red light. And as you heat the star up, you get more of other light. But when you go to a certain high temperature, all the light comes out in the ultraviolet, so we're actually missing stuff. And actually, if we had a different atmosphere and we could see through the ultraviolet and the infrared, stellar astrophysics and history would be different, because we would have been able to see this without ultraviolet and infrared sensitive eyes. But it's just because the atmosphere we have and the star we have that this is how our eyes evolved, and the chemicals in the cones in our eyes can detect color, which is kind of amazing. But we can use these lines and these patterns. So if you actually imagine now with this color scheme where I'm going from red being cold to black and blue being hot, I can now look I can take these actually model atmospheres. So these are where I put all the physics into an atmosphere to make a model, and now I can take a photograph of them. And so with the same spectra, you can see that now we've got those very strong lines for the hydrogen in the A star. They become weaker in the B star, weaker in the O star. And as we go down with the F line, you can suddenly see how you get this extra line, which changes the way you would see them. You've got the G stars, where that doublet that gives you the funny shape that we saw on the photograph a minute ago. And then you go down to a K and M star, and there you actually get even more lines, because there's actually just more atoms around to absorb the light. Just trying to remember where I am now. Okay. And the thing is, here we've actually still got them by the quite broad categories. The fact is, each of these categories has like 10 subdivisions. So you can go from a B0 star to a B9 star. You can only go as hot, I think, as an O2 star. Now, when you're looking at this, you can actually see the patterns. When you look at that photograph, you could look at the pattern. What's amazing about Annie is she could do 3 a minute down to like sub-classifications. So she could tell you B9 and also probably whether it was a giant, what the gravity was just by looking at the atmosphere, because she recognized them almost like fingerprints, which is pretty amazing. Now, today we use computers and we try and do it automatically, and there's all this fancy stuff to do, but to do it as quickly as she did, it's quite amazing. And of course, the other women were able to do that as well, but she was the fastest all her life. She was also deaf, and some people reckon that she actually just could concentrate much better than everyone else, because nobody could shout at her and actually listen to her, which sounds kind of appealing. I mean, this is why I have noise-cancelling earphones today. It really helps. Okay, so Annie came up with the scheme, refined it, but then how do we actually work out what stars are made of and their temperature? Because I've already indicated that these lines tell you something about what's in the star, what the actual chemical composition is. But if they're made of all the elements, which they are, why do we not see some lines? And if the stars are all made of hydrogen, why do we not see hydrogen in some of these stars? It's an interesting question. So one thing to know is if you look at the emission or absorption spectra of every element, you get this wonderful plot. I absolutely love this plot because it looks complicated, but it's just showing you that every atom has a different number of lines of color that it either absorbs or emits, whether it's that absorption spectra because it's absorbing light from something that's hot, or it's emitting light because it itself is hot. And, hydrogen has this magnificent red line. Helium is quite nice because it's got this extra orange line. Mercury, so if we had fluorescent lights here, which you probably don't because you've all upgraded, so there's probably no dangerous mercury here. What's the chemical element for mercury? It's Hg, isn't it? Yeah. I've lost it. I've lost mercury. Not the planet, the element. It's okay. Sorry. Second from the left. Oh, there we go. Okay. Thanks. So mercury is interesting because that's the vapor that's in most fluorescent tubes, because it emits something that's almost like white light, that then you put the powders inside and it takes the mercury emission lines and makes much more pleasant white light, if you didn't know that. Now, of course, we're all using LED lights, so that's a really pointless piece of knowledge. But, what's the point of knowing pointless knowledge if you don't use it? And, if you've ever seen flame tests when you was at school with chemistry, this is why they have different colors. right? And so you can literally do this, and chemists use this to work out what different stuff is made of, of the flame tests. They probably don't anymore because this is dangerous, but it looks pretty. So to actually go into this, we need to take a sidestep into another physicist, who is Meghna Sahar. So this equation, this is why I think these stories and telling the stories of people is important. Because when I did fourth year undergraduate stellar structure and evolution, right, we learned the Sahar equation, right? We learned about mixing link theory from Böhm-Vitense. We never knew about these people, right? And so you're assuming every physicist and every astrophysicist is like the people you see around you, which when I was growing up was a white man, which is not anything bad, but it's, if there's only one voice telling you things or making things up, you're kind of missing out other stories around. What's interesting about Meghna Sahar is he came up with this lovely equation. Isn't it lovely? So I should actually explain it, maybe. Basically, it's saying the ratio of things that are ionized, how many electrons are in an atom or outside an atom, is proportional to some quantum mechanical factors that we don't worry about. We just wave our hands. But there's this other exponential factor, which is to do with temperature. Basically, if you heat material up, it's more likely to get the electrons outside an atom than inside the atom, because basically you heat up your atom so much that the electron jumps out. This was the first time he formulated. Now, why is this key? Because we've got that stellar temperature range. How can we work out what the temperature is? And why isn't there hydrogen in all of them? Because we know stars have all hydrogen. So let's take an example of applying this equation to helium. I should also say Meghna Sahar was interesting because he was an astrophysicist, did that equation, and eventually kind of gave up and went into politics, and actually produced many of the civil infrastructure projects across India, which is kind of cool. You get bored of astrophysics, it's too easy, go and become a politician. No, I haven't got any ideas, in case you're wondering. But let's look at helium. So helium is an interesting atom, and it's got 2 protons and 2 neutrons. And here you've got 2 electrons orbiting it to cancel out the 2 electrons. It's electrically neutral. And that's nice, because now you've got this helium gas, it will give you a funny voice, and you can just sit there and it's going to produce lots of lines in the spectrum. It's going to give us those lines we just saw in that nice periodic table we had a minute ago. Let's heat it up a bit. And as you give up more energy, some of these electrons are going to jump out. And so your helium lines will be weaker because there's fewer electrons to give you the strong lines. If we heat it up again, more electrons come out. You've still got now actually hydrogen-like atoms where you've got a helium nucleus with just 1 electron. So again, you actually get a different spectra because because the lines will be different because the atom is different. And if we heat it up again and then again, we've actually got no electrons in the atoms. They can't produce lines. This is actually what's happening with hydrogen as we go from an A star, which has got lots of hydrogen, lots of electrons in those hydrogen atoms, so you can see really strong lines. But as you heat up, as you go above 10,000 degrees Kelvin, you're ripping the electrons out of the atoms. And if you don't have electrons in the atoms, you can't produce the lines. And what happens when you go to cooler temperatures, for cooler stars, you've still got the hydrogen there, but then when you've got hydrogen being the strongest one, all the other atoms that would give you lines have lost electrons. And as you go to even cooler temperatures, those other lines then dominate and give you stronger lines than the hydrogen. And the only way you can work this out is to actually work out the amount of stuff there is and how many of them will be visible. So you can have as much hydrogen as you want or much calcium as you want, but you may not be able to see anything. And the person who used Meghna Sahar's equation to do that is Cecilia Payne. Now, bearing in mind this is in the 1920s, and this is when we thought that the sun was made of the same stuff as the Earth. So the sun was just a big ball of iron or something, or it had the same composition as the Earth, so it would actually be mostly silicon and oxygen. This is the first, number 1, first PhD thesis from Harvard. And it's got a great title. Isn't this like the title? This will make you get out of bed in the morning to read this, or Stellar Atmospheres, a contribution to the observational study of high temperatures in the reversing layers of stars, or stellar atmospheres. And also this is because I was actually at a conference again at Carnegie Observatories, and they allowed us to go to the Huntington Library in the area in Pasadena. And, they got out like a version of Kepler's, Copernicus's works, Kepler's thingy, and also this. And so we had all these really nice books out, but this was the one that captured my imagination because, you know, this is where Cecilia Payne basically says stars are made of hydrogen. Because when you analyze how strong the lines are, what you should be able to see from the hydrogen lines you detect is that basically you know there's actually very little hydrogen there. A lot of it's been ionized, which is why you underestimate the amount of hydrogen and why you can overestimate all the other elements. The great thing is that the PhD examiner said, oh, it's a load of rubbish. That's true. The sun can't be made of hydrogen. It must be made of iron and oxygen and things like the Earth. And so she actually forced her to rewrite her thesis saying like, yes, but obviously the result is wrong and should be untrue, right? But then that guy then wrote a paper a few years later saying, oh no, I was wrong. And yes, the sun is made of hydrogen, but didn't reference Celia's thesis. So now everyone does know it, and we've forgotten this story, but it's kind of annoying. And actually, if you go, the thing that I always get really excited is you go to a table here, which actually has the values of the abundance of the sun in those days. And it's actually not too bad. It's actually quite close to what we actually still see today, although we don't actually know what the abundance of the sun is. I mean, we know it's all hydrogen, but the metals are actually something that's still under discussion because it's actually really complicated to model. But yeah, if you go and look at this table, it's what it should be, which is quite exciting. So it was Cecilia Payne in those days. Then she got married to someone else, and so it's Cecilia Payne, another astronomer, and they actually worked on this quite a lot and did much herself. Okay, so what have we got so far? We've got stellar spectra, so we know stars have different types. We know how to work out what their surface temperatures are, because also the other thing that drops out of this is if you know the composition and the surface temperature from using Sahar's equation, you know the temperature, you know the composition, you know everything about stars. But you don't know how massive they are, and you don't know how far away they are, which is really key to actually working out how bright they are and how efficient they are at burning their nuclear fusion fuel. Nuclear fusion, us realizing that it's got to be nuclear fusion, is another story to do with other people, with Arthur Eddington, and with, it's a long story, so I'm not going to go into that now. Yes, the only way we can, I should really take that off and see if anyone can guess this binary star. But anyway, this is Sirius A and B. It's a binary star system, and we knew of binary star systems back then in the 1920s, because if you look at Sirius A and B, it's got a 50-year period, and people were actually observing its relative position over time as they orbited around each other. So we did know that binary stars existed and orbited around each other, which was nice because we could see this one. It's got a large proper motion as well, which is why it's got that apparent view. And of course, this is all prior to 1920, which is all nice. But the number of stars we can see in this way is relatively small, right? Because there's not that many stars close by and you need high resolution. And back in those days, we didn't even measure parallax. I think the first actual parallax wasn't measured until 1955. Someone may correct me on that. So we wanted another way to find out binary stars, because here you can actually work out the mass of Sirius A and B. You can do it in a few lines. Sirius A, the main sequence star, is about 2 solar masses, and Sirius B, the white dwarf, is about 1 solar mass. And so this goes back to this photo and Antonia Maury, because she discovered the first radial velocity variable that was a binary star. And this is today one of the best ways we can detect most binary stars. You can detect them from eclipses, but that's only a small number because they've got to be perfectly aligned to our line of sight. But here she was able to actually see, this is what I like about this, even then scientists were putting up on their wall their latest results. And you can see how over a period of days, you've got from the measurements of the radial velocity, a clear binary star there from Beta Auralgi in December 1889. I'm just wondering why that's decent, because that's not in 1989. I'm just wondering, that must be from the original one, or from data maybe taken back then. I'll have to go back and actually reread. I've got to reread the entire book now. That's okay. But it's the first radial velocity diagram for a first spectroscopic binary. So this is actually how we can discover binary stars that I know and love so much today, and it's all come down to Antonia Maury, which is kind of exciting. But this is the kind of stuff that they were doing. They weren't just analyzing data. They was able to see funny stuff and stuff that made them go, oh, that's interesting. And that's why, it's like the women as well. I mean, okay, so Edward Pickering ran the project, gave them all things to do, but the discoveries were theirs. They were the first ones to look at these things and go, oh, that's kind of interesting. Spectroscopic binaries are where you've got the lines from the absorption of the two stars, and you can see them shifting. Normally we only see one star, but sometimes if the two stars are of similar luminosities, you can actually see the lines doubling as they go round, and one orbits towards you and one goes away from you. So this is nice. This actually gives us a way to weigh the stars and work out what their mass is. But what we also need to do is make sure that we have their distance, because that enables us to work out how bright they are. That's actually difficult, because again, in these days, we didn't have parallax. So, so I'm sure everyone knows about Cepheid variables. Does everyone know that it was Henrietta Leavitt that noticed them? And it's interesting because I think Harrow Shapley had some letter about, like, should she be nominated for a Nobel Prize or something for discovering this? And he said, like, well, maybe, but also you could give it to me instead. But Harrow Shapley did enough other stuff that, he's worthy of good discussion. But what Henrietta Leavitt noticed by looking at stars within star clusters, which are varying, because if you're looking in a star cluster, all the stars have the same distance. And she noticed that some of them were varying, especially those in the other, like, Magellanic Clouds, where you would see more of these stars. And so this, along the x-axis, is the logarithm of the period of oscillation, so how long it goes from being bright to dim to bright again, versus the apparent magnitude. And actually, with these magnitudes, these must actually probably be in the small Magellanic Cloud, I think, or the large Magellanic Cloud. I can never remember. But yeah, so this is at 1 day, sorry, this is at 10 days, and this is at 100 days. And you can see how much brighter they get. And so the idea is here is if you know the oscillation period, and you can measure how bright the star is, and you know that it looks like it's a 1 watt light bulb, but you know it's really a 1,000 watt light bulb, you know it must be further away from you. And so that's actually the key to unlocking the distance to other galaxies, because today we can actually look at stars in other galaxies, and the entire distance ladder basically depends on this diagram. Because we can resolve stars in other galaxies, and so, for example, when Edwin Hubble was trying to work out if other galaxies were galaxies or if they were just within our Milky Way, when he saw a Cepheid variable within M31, I think, the VAR plate, he was able to work out the distance by using the Cepheid law relationship. That's how powerful this thing is. And now with the Hubble and with JWST, especially now JWST is on the scene, people will be trying to push the Cepheid distances as far as we can. Because again, it's the most accurate way of measuring these distances. Okay, so we've done a lot of observational work here, which is nice. And now I've got like maybe 10, 15 minutes to get round to the end to actually try and use these observational details that we've known for many years to try and understand these stars, to understand the evolution of stars and of galaxies, which is the last two women I want to talk to about today. And so the first person is one person that nobody will know. It's Erika Böhm-Vitense. So what's wonderful is when you go through stellar evolution theory and structure when you're an undergraduate, stars produce energy in their cores and it gets transported to the surface. And it gets transported by radiation, basically that there are photons like being produced. In the interior, they're of course very hot. And if they get to the surface, they escape and come into our eye. The other way it gets going is that sometimes within the star, certain structures or things happen that make it easier to actually take the material and just shove it, right? So if light's too slow, you're going like, but light travels so fast. It's because light has to bounce between collisions because there's stuff there. But sometimes you actually have convection going because it's just easier to take the hot stuff, it rises, and then it cools down and releases it to the next layer. And so you can see here this diagram. For example, our sun in the middle has a radiative interior, so the energy is produced in the center and transmits outwards through photons until it actually starts getting to the point where you start forming hydrogen atoms and you start recombining hydrogen, and so the opacity goes up and it's quicker to move energy to the surface by convection. So the surface of the sun is convective. If you go down in mass, everything's convective. And if you go to more massive stars, it's got a convective core and a radiative envelope. Now that's great. Now the beautiful thing is when you try and model how energy is transported by radiation, it's really easy to do. You've only got to worry about photons, you've all got to worry about atoms and how they scatter things, but basically it's just electrons that do everything. It's absolutely so easy to write down, and it makes perfect sense because it's just light shining. It's easy. Convection is hard, because you've got hot stuff, And you've got to think, okay, so you got this hot stuff. If I pull it upwards, does it keep on rising? That's an easy answer to ask. Sorry, that's an easy question to answer. So yeah, if you can actually look at material and say, basically, if I move this blob up, is it less dense than material around it? Yes, okay, it keeps on going. So whether a thing is convectively stable or unstable, so it has convection, is easy to do. What's hard is to work out how fast you transmit energy. Because you're talking about convection, so blobs of material moving. So that means it's a fluid dynamics, it's a hydrodynamic problem. You've got hot material made of really gaseous stuff we don't really test. And you've got to work out, okay, so how big are these blobs? How far does it raise in the atmosphere before it like stops and sinks again and releases its energy? And, you know, how does this work in a spherical symmetry? You know, it's one thing to like boil water on a stove and have the convection currents in the water. It's another thing to have something the size of a star and trying to look at what the convection is doing. And so we have something called mixing length theory. It's called mixing length theory because basically you say, okay, so those blobs that come up, however the pressure, which is like something to do with the density is varying, or how quickly the density and pressure vary and the temperature vary within the star, you know, we'll say like the thing goes 2 pressure scale heights. So basically if the pressure or the density varies by a factor of 2, then we'll say that's how long the cell actually rises and stops, and then another cell would stop and start off. And that's the one free parameter node we actually need to work out, but we can't. So what we do is we say, okay, we've got this free parameter, we know how big the sun is, we know where the convective zones are from the sun, and so we'll tune this number that we don't know to what we see in the sun. And that's where we get, it's actually a value of about 2, I'm not lying. And we then apply it to all stars, which has got to be true, right? We can't be wrong with that. Reader, we are very wrong with that. But where does mixing length theory come from? Well, if you go to all the papers, there's this paper by Böhm-Vitense that's in German. So nobody ever reads it because it's in German, unfortunately. But nobody ever told me it was Erika. Now, this seems stupid, but when you've gone through a series of papers and stuff where you've got Meghna Sahar, you've got Arthur Eddington, you've got Lord Kelvin, you've got, I'm trying to think of all the different names. Yeah, Carl Schwarzschild. You get a bit bored because you're thinking like, oh, okay, only men do theoretical stellar evolution. And nobody actually mentions, oh, this is Erika Böhm-Vitense. And suddenly you actually see something in a different light. Now, this is, of course, important for me because I used to think like, oh, you had to be a man to do astrophysics. Turns out, no, it's just hidden from you. And that's why these stories are important. Just to, I mean, it's not that big a deal when you think about it, and it shouldn't be. But unfortunately, just the way that things are reinforced as you go through, especially when I was growing up 30, 40 years, well, okay, 30 years ago, you know, this is actually kind of a remarkable thing. And then you find out she has a series of stellar evolution textbooks, all written in English, so you can actually understand it and understand that this is the person that tells us how energy is transported in the surface of our sun. And I think that's really powerful, especially since I'm a stellar theorist. There is also a really great interview of her. Okay, and this is another reason that gets me really excited. So she's describing how you would make these models on early computers. So a lot of this stuff was actually done by hand. And if you look at the book by Martin Schwarzschild, there's an appendix at the end telling you how to compute the structure of a star by hand using slide rules. Now, Erika was one of the first people to use computers, and she remarks is she could tell what the computer was integrating because it would start at the center of the star and integrate out to the surface. And she could tell by the sound that the computer made whether it was integrating through a radiative zone or a convective zone because the physics was different. Now, you can't do that today because computers do it in 30 seconds flat, and it's like each iteration takes a thing could ever do it, and they don't make noises unless you want them to. But it's just, you know, this kind of interesting connection that, you know, you could see yourself trying to understand what the computer was doing because you'd have to wait hours and you'd have all these punch cards and then you'd have to try and translate them. So I think that's kind of exciting. And she had so many papers beyond just coming up with this mixing link theory, but it's this wonderful paper that she had. Anyway, so again, so just talking about Erika's work, it's understanding the surface of the sun. And when you actually look, this is kind of shows you the problem, right? Look how complicated the surface of the sun is. But she was able to reduce it to a few simple equations that work and still work. And while, you know, we use this mixing length of 2 and we shouldn't apply it to all other stars, it doesn't do too badly, right? So you can take the number we derive in the sun and also use the same equation in the surface of trying to understand Antares, which is a red supergiant. Right? The same physics applies across the scales of the solar system. which I think is kind of exciting. But of course, Erika also gave us the ability to make stellar models, which is what I really do. So here, this is a color magnitude diagram of basically mostly convective stars. But here, these points are, does anyone want to guess which cluster that is? Surely you can recognize a cluster from a color magnitude diagram. Yes, the Pleiades, thanks, Scott. Yeah, I've shown this one before, yeah, or Matariki. And these dark contours in the background are what the models predict that you get using mixing link theory and all the other physics we have from all the other theorists that there have been. And so we can actually understand the star clusters by comparing them to models. Okay, so the last person to get to is Beatrice Tinsley. So she then takes this work of stars and applies it to galaxies. And this is what I really like. I read this, and she's trying to study elliptical old galaxies. And basically she apologizes almost in the abstract to the reader, saying or in the introduction, saying something along the lines of, yeah, I want to study elliptical galaxies, but unfortunately I have to model spiral galaxies first because they evolve into elliptical galaxies or younger galaxies. But it's always a thing that when you're trying to do some theoretical thing, normally whatever you make will have other applications. But what did she effectively do to be able to actually understand older galaxies? And this is where we actually then have to go and do a little bit of what color magnitude diagrams look like as they age, which is kind of what I was just showing you here, right? So here's your color magnitude diagram. The models are over 100 million years old, so you know Matariki is about 100 million years old. And what, as I said, Beatrice wanted to study was these elliptical galaxies. In that paper, she studied many things. And so these are very old because they're all red old stars. But, if the galaxies are all red and old, they must have one day, or earlier days, looked like spiral galaxies where they had a mix of young, old stars. And so we can start with just looking at some stars, right? If you've seen this before, this is my favorite way of explaining stellar evolution. So this is a collection of stars, also represented by Lego bricks. So if you want, you can go and get some Lego bricks and use these. It's great, right? So what we do is we take a collection of stars we just observe in a cluster or in the night sky, and we double them, and then we arrange them by temperature. So we use the spectral lines, actually, that Annie Jump Cannon came up with, to put the hot stars with weak hydrogen, then going to hydrogen, then going to other lines, going from hot to cool on the right. And then we arrange them by luminosity, and so we've got our Lego bricks or our stars up this direction. I actually did this in a lecture once. I just threw all the stars, all the Lego things on the visualizer, and then slowly put them in the way that you would do, and it was quite good fun. And then we can see that stars evolve. So the most massive star will leave what we call the main sequence and become a red giant, okay, or a Duplo brick. And then eventually that thing will explode, and then we go through, and stars keep on trying to become red giants. And you can see that the main sequence gets shorter and shorter. But you can see the colors of the stars are changing. The color of the population of the stars is going away from blue, going to red. Okay. And so eventually you get to a very old cluster where they're all red. But you've got some red stars that are brighter than the fainter stars. Now, what I like about this is Beatrice is also one of the first people to then use this technique of looking at galaxies with supernovae in them. So you see a transient event in a galaxy, and then you go back and you look to see, what was the star that exploded, trying to understand it from its stellar family. Okay, what other stars are there? And so she wrote this wonderful paper, What Stars Become Supernovae? And she gets the right answer. She basically says that type 1a supernovae are coming from low mass stars because they're happening in ellipticals and spirals. But then the type 2 supernovae, which are called collapsed supernovae, are coming from younger stellar populations. And so actually, you get the masses wrong, but they're about there. And also, she doesn't realize that there's different types of type 1 because we didn't know back then. But obviously, the type 1as are dominated. Type 1as from the white dwarfs and the low mass stars dominate the type 1 supernova rate. But that's kind of exciting. And so this now gets us to the point where we can talk about gravitational wave transients, at least I hope it does, in 5 minutes. Okay, good. And so what can we do with this today? What can we do when we try and bring all of this together today? So, you all know what this galaxy is, I'm sure. Okay, it's NGC 4993. It's an elliptical galaxy. It's quite boring. It's really boring, in fact. You know, so if you do a Google search for how many people search for this galaxy, it's like there was no Google searches before 2017. And in 2017, you see this huge spike. It is the worst kept secret that within this galaxy, a binary neutron star merger happened, where two neutron stars merged. There was a kilonova, which is a bit like a short gamma ray burst, and we saw it. Yeah, so the Hubble Space Telescope Twitter bot tweeted, looking at binary neutron star merger. So everyone knew. But the LIGO Virgo Kagra, and is this being streamed live, or is it only to members? Okay, yeah, I can tell these things. Got very upset, right? Because they knew about it. They couldn't say anything or confirm anything, but it was on Twitter because someone forgot to turn the Hubble Space Telescope Twitter bot off. But they found it. And otherwise, it's a quite plain, boring galaxy. But what this is just, you probably heard of GW17 or 17 many times before, but I like trying to look at the fact that it's one of those events that true multi-messenger astronomy doesn't happen very often. Now, of course, it was really began back when, Hess went up in an air balloon to detect cosmic ray showers. You could argue that's when multi-messenger astronomy began. But what I mean by multi-messenger astronomy is using like electromagnetic and gravitational waves, using electromagnetic and neutrinos, right? We now have this. We haven't yet had the triple of having gravitational waves, electromagnetic and neutrinos. When that happens, everyone will get really excited. But all we had here is up here you can see the gravitational wave track, the chirp of the binary stars going whoop, as they do. You've all heard the chirp before? Yes, okay. If you say no, then that's okay. 2 seconds after the two binary neutron stars merged from the gravitational waves, we see a peak in the gamma rays. It's a gamma ray burst because you formed a black hole with neutron-rich material flying around the black hole, which would have relativistic jets coming towards us. We was luckily aligned to it. Later on, we saw the X-ray source. This is the center of the galaxy in X-rays. We can see here the source as it cools down. We also got it in the optical, in the radio and infrared. So even today, we're still actually picking up what's going on with the radio waves, I think. I haven't checked, but I would assume that it's still actually quite bright in the radio waves. But this is why people got so excited, because we saw it in every possible wavelength. And it's something like a third of the world's astronomers knew about it, which was really bad for the 2/3 of us that weren't into it, because we felt really left out. And some of the paper lists are just ridiculous with the number of people on it. But it's a really exciting event. So we learned so much from the event itself because we can study it in this detail. But what about the galaxy itself? So that's where we are. And this is the work that Heloise Stevens was actually recruited to Auckland to do. Because Marsden gave me money to try and understand that host galaxy using the binary star models. But really doing what Beatrice did, looking at the stars and working out, okay, how old are the other stars? What is the mass of the progenitor? Like how long ago did that binary neutron star form in supernovae? And so you can read it in detail. It's now published, and I clicked the final report on the grant today. So this is now over, which is kind of exciting. But again, we're going back to doing effectively what we've been doing since the Harvard Computers times. This in the grey line is the observed spectra from the galaxy. It's not of an individual star, it's of a bunch of stars. But what's interesting is when you go down here at these long wavelengths, 750 nanometers is like the infrared. These really big bumps you see here are actually titanium oxide bands. It's dominated by the red giant stars. So we're almost actually here with all this age information dominated by actually looking at the brightest stars in this galaxy and trying to integrate them together, still using those stellar classifications. And actually it's quite model dependent because whichever spectra you use, you don't know if you've actually got the right answer or not. And then you've also got this Balmer break up here, which tells you something about the hottest stars you actually have in your galaxy. But if you take this spectra up here, you could, down the bottom, turn it into the light fraction. So how much of the light is how old? And also what we're really interested in, the mass fraction. How much of the mass of the stars are at different ages. Now these are logarithmic ages, so 8 is about 100 million years, 8.3 is 200 million, 8.5 is like 300 million. But we've seen there's a little bump at about 1 billion years, but otherwise most of the stars in the galaxy are 0.0, sorry, that should be 10.0. I've never noticed that that's wrong. About almost 10 billion years old, so almost as old as the age of the universe. And when you looked at what people had done before, then they all had this bump at like a few million years. We find nothing younger than about 500 million years. There is just no stars, and even then there's a bit of light there, but there's practically no stars. Most of the stars are billions of years old. And so it really suggests that the binary neutron star merger we saw is most likely to have come from this very old population, which is actually different to what other people have been assuming. And when we look at other binary population synthesis codes, they all suggest that binary neutron star mergers have quite short delay times. Now, this is only one, so we have no idea what's going on. But Heloise actually was on a recent study that didn't see the gravitational waves, but they found another kilonova, and again, it was quite old. So within the next year, we should actually know, are most galaxies like this, or is there a spread of ages? We really don't know. But we can go back, we can look at the galaxy in detail, we can track where the ages are, which is quite nice. So you can actually look at, like, the older bit is at the center, the younger bits are just everything else. So you can actually track back to where maybe the system was formed. You can make stellar evolution tracks. So this is basically using similar stuff to Erika Böhm-Vitense, where you're trying to now work out, okay, how did the stars interact to get to the point of forming the binary neutron star merger? And then you can work out even their initial orbits and many things about the stars by trying to use that age constraint that you've got to understand more about where the stars came from. And the fact it took 10 billion years for these stars to merge, because they would have been formed, the two neutron stars formed within a million years of formation, and there was in a perfect orbit, such an orbit that it took 10 billion years for them to merge, so we can see them today. Yeah, so we can actually use all that together, right? So we've used the stuff to do with anti-jump cannon, and Cecilia Payne and everyone else to try and piece together, or to put all their material and all their thoughts together to make this one big finding that basically reproduces what Beatrice Tinsley did for supernovae, but now for a binary neutron star merger. Okay, so that was a lot of information. I'm sure everyone has questions, maybe need to sleep. So I will leave you with the final title slide, and thank you very much, and I'll be happy to answer any questions.
Really interesting talk. Heloise actually did a talk for us here, so some of the people here will know her. Is she still back in?
She's back in the UK. She's writing, if you know about LSST, that telescope that's 8 meters across and it's going to be taking a movie of the sky every night, she's writing an AI astronomy bot, I suppose, to try and type the transients it sees automatically. It's really tough. She's having good fun.
Okay. So we got any questions from the audience?
You showed how so much heat makes the outer electrons fly off. Does that affect other colours on the spectrum as well, or is it mainly just around the
it affects everything over the entire, so it's all atoms over the full wavelength. And some of the fun things that happen are like, so the fun is, if you look at the hydrogen surface of our sun, you might expect it to be quite ionized, because it's quite close to the place where it does ionize. But actually, you've got H- ions in there. There's actually enough energy you can have in a hydrogen atom with 2 electrons. And it all comes back to actually using Sahar's equation to try and work out how many of these different things are. But you're right, it's not just for hydrogen, it's not just for helium, it's all the elements. And if things get really hot, for example, if you have an accretion disk around a black hole, that material can get so hot. If you have iron there, iron can be ionized, and so it's only got a few electrons going around the nucleus. And what happens is you take electrons out of a nucleus. If it's got all that positive charge, the electrons actually go around faster and faster and faster, and you actually shift the electrons so you can actually see the ionization state. And you can see emission lines in the X-rays because of the highly ionized states of iron. So I've kind of glossed over it here, but it can get really fun and complicated as you get things really hot.
So do they have to normalise the values that they read?
Yeah, yes. And there's like big lookup tables and you can calculate them. But actually it's even more fun because sometimes the physics is so extreme, we get the wrong answer. And actually there's two, like what we would term photoionization codes that works out what the stuff would look like. And if you use different model atoms, you get different answers. So it's kind of exciting. So yeah, it is difficult when you get really hot. Cold stuff, it's easier, but you have to take a look at everything at the same time.
Are there any good examples of completely red clusters?
Yes, so if you go and look at globular clusters, they should be red. It depends also how you're looking at them. So things like, is it 47 Tucani? There are things that are really old. They're redder than most, but not that red. You probably, in the far future, in a few more 10 or 20 billion years, a lot of clusters will suddenly become very red. There's actually a simulator where you can actually take your synthetic cluster, simulate it as if you're looking on telescopes, which I've done over all the different ages. And it is when you go beyond about 30, 40 billion years, then the clusters become really red. So there's nothing actually that red today. Normally, for example, if you look at something that's got a 10 billion year lifetime, that's where the sun is at the main sequence turn off. So you'd still have white stars, which effectively the sun is white. But if you go beyond that, that's where you start. Give it a few more billion years, and yeah, we'll have red clusters.
I guess most of the open clusters, that'll never happen because over time they dissipate because of being in the plane of the galaxy. Stars get lost over time.
Yeah. But then the galaxy will be red. So, elliptical galaxies are effectively one big giant globular cluster. But it's a merger of all those ones. The globular clusters are just the clusters that have been massive enough to survive, maybe. But yeah, star clusters are an entire another talk. There's a question here. Yeah.
So when you showed us the slide of the different suns with all the different masses and stuff, and how they have the different zones and of convection and radiation and whatnot.
Yeah.
For the blue one, the biggest mass. Yeah, that one. How is the convection happening in the core of the star? Where's the heat?
Well, the heat's generated right in the center. So what happens? So the reason for this is fun. So when you go down in mass, the stars become fully convective just because the material is so cold. It's actually really opaque, and so the photons have trouble to get out. So it's just quicker for the entire star to generate the energy at the center and move it to the surface. In the hotter stars, what's actually happening is the energy generation switches from the pp chain, so smashing protons together to form helium, and goes to the C&O cycle, which is where you put a proton onto carbon, which forms nitrogen, and then you go around forming nitrogen until you get to nearly forming oxygen-16, but instead you knock a helium nucleus off and you go back to carbon. And that catalytic reaction, even though it takes over in these more massive stars, it's got a higher temperature dependence. And so it's even more constrained, even more tightly to the center of the star, and it's producing so much energy. The only way to get the energy out is by convection. So actually it's a different way. It's because it's producing so much. So it actually just rips out. And then eventually it gets to a point where the temperature drops and it becomes inefficient to get convection. And so then the rest of the star, the energy transports by radiation. Now, the fun thing is that the changeover about 1.5 solar masses, the cores are very small. And as you go up in mass, they go up to maybe about 10% of the size of the core. But as you go to more and more massive stars, when you get to a 100 solar mass star, the central core is about 80% of the mass of the star is convective, because as you go up in mass, you're producing more energy, which has bizarre consequences. Because then if that 100 solar mass star, 100 times the mass of the star, is losing mass, eventually you actually expose the burning products while the star is still on the main sequence, which normally you wouldn't see to a red giant. So it's kind of good fun why you get this, but it's basically with these really massive stars, they're producing so much energy, it's the only way to get the energy out fast enough.
Then how come the smallest one is also just convection?
So it's like either energy production, making it convective, or it's that radiation is being impeded in some way. So both in our sun and in the low mass stars, they're at such a temperature that photons can't do it. There's actually too much material in the way, too much opacity for the photons to do it. And so it's quicker to basically the star says, okay, I give up, and just shoves the stuff. But this is something I've been working with she's a PhD student in America who's asked, she's got a study of low mass stars and just wants to know the size of the convective cores. And stars don't really become fully convective to about 0.3 solar masses. But she has observations of this, so now we're going to try and test the models and the depth of the convection zones with the observations she has, and it's quite exciting because it's something I'm sure we've got right, but we don't know. And if we haven't got it right, then that's quite revealing, and it tells us something about the opacity law or the energy generation.
I don't know if it's correct, but I remember hearing or reading something that if you took you start off with a gamma ray photon in the sun's core by pure radiative transfer, that energy will take thousands of years to reach the surface.
Yeah, something like about 50,000 years, yeah. So you're looking at stale sunlight, yes. All stars, you're looking at stale starlight. It's been in the cupboard for a while. And it's because there's collisions going backwards and forwards. And basically the way you model it is the temperature of the material determines what photons you have. So yeah, at 10 million degrees Kelvin at the center, it's basically gamma rays and other things. And of course it slows down as you go out. In the center of really hot stars, you can, this is just a cool fact, just to pass on. But if the temperature gets to like billions of degrees Kelvin and the density is still low, which happens in some stars, you can get electron-positron pairs because the two photons are so hot they can collide, produce electron-positrons, and then recollide to get you photons, which is fine, except sometimes when those two electrons and positrons recollide, they produce neutrinos, and so you lose your photon pressure, which actually holds the star up and the star collapses because it's so hot with the photons. See, stellar physics is great. I could go on about this for hours. There is an exam next week, right? If I'm doing dynamic universe to the 4th years, and the exam or the test is the week after next. So if anyone wants to come along, let me know. Oops.
There are lots of giant stars. Are there any giantess stars?
That seems you want to give your stars gender. I'm pretty sure most stars are agender. Yeah, or non-binary. But I normally talk about binary stars, so I shouldn't talk about non-binary stars.
We've got any online questions, Steve?
None today.
Okay, are there any more questions? Not, I'd like to thank Jan for coming along and presenting a really fascinating talk. Got a little gift from the society.
Oh, thank you.
Thanks very much.
Thank you very much.